Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asgar, and today the topic of our discussion is synthesis and design of inorganic materials under the subject of advanced inorganic material chemistry. Dear student, so far we have studied some of the important methods for the design and the synthesis of important inorganic compounds. In last lecture, we have studied about the synthesis of graphene, which is very important compound in recent sciences. It is equally interesting for the chemist as well as a physicist. They both scientists working on the designing of graphene for the betterment of humankind. Due to its interesting applications in the field of chemistry as well as in physics, it is actually most hoted research in the world so far. So the synthesis of graphene is also accomplished. We have studied and also accomplished by the designed method of for the synthesis of inorganic compounds. We have studied even that the most important one was the hydrothermal or solvothermal synthesis, which would be quite helpful for the successful synthesis of graphene. Today we will talk about synthesis which is quite difficult made possible by chemidos methods, which is barium bismuth ferrate BiFeO3. It is actually the example of a difficult synthesis which should be synthesized by using chemidos methods. We have already studied some of the important aspects and the steps of chemidos methods, and we also synthesize some of the renowned compounds by using this method. BiFeO3 is a material of great interest since at room temperature it is both ferroelectric and antiferromagnetic, and is a rare example such as of multiferric material which offer numerous possible applications involve coupling between the effects of electric and magnetic fields. Due to its highly desirable properties, it is imperative to synthesize BiFeO3 in a comprehensive way. The properties which is actually shown by BiFeO3 is very interesting because it actually showing the ferromagnetism and antiferromagnetism and even the multiferric properties at room temperature. We know that there are so many materials which have these kind of properties, but the real problem is these properties should exist at room temperature or above room temperature. But there are many materials which actually possess this kind of properties but at low temperature. Low temperature materials did not catch the eyes of scientists because of its non availability for the useful applications in the field. So these kind of materials like BiFeO3, which have the interesting properties of multiferric, ferroelectric and antiferromagnetic at room temperature, is quite interesting. The synthesis of high purity samples of BiFeO3 by solid state reaction is difficult since small amounts of impurities phases. The impurities may be Bi2Fe4O9 and it may be Bi25Fe039. These are often present even after many heat treatment cycles. So these impurities actually contaminate our desired product BiFeO3, and even they persist and may present after performing many heat treatment cycles. The difficulty in solid state synthesis can be understood from Bi2O3 Fe2O3 phase diagram. Although BiFeO3 appears on the phase diagram as a thermodynamically stable phase, it is not particularly stable and melts at about 933 degrees Celsius to give Bi2 Fe4O9 and liquid. The phase diagrams also exhibits that of three bismuth ferrite phases, which is Bi2Fe4O9 has the highest melting temperature and it is supposed to be the most stable one. The driving force to form pure BiFeO3 in mixtures is rather small and explains why phases such as Bi2Fe4O9 are difficult to eliminate once they have formed. Moreover, the problems with solid state synthesis of BiFeO3 concerns the volatility of Bi2O3 on heating at temperatures between above 800 degrees Celsius and variable valence state of iron leading to other possible unwanted side products. Many chemidose methods have been used to synthesize BiFeO3 and all make use of either fine scale reaction mixtures or single source homogeneous precursors. For example, fine scale mixed hydroxide precursor is obtained by hydroxide precipitation from aqueous nitrate solution. Here we can see that Bi3 plus and Fe3 plus in the presence of hydroxide mix together, react together and change into bismuth hydroxide and iron hydroxide BiOH3 and FeOH3. The hydroxide precipitate is filtered, dried and then decomposed by heating. Co-precipitation is a simple method, but it can be difficult to achieve precipitation of both components simultaneously as fine scale mixed precipitates. Thus, if the component hydroxide may precipitate, which is actually the opposite of the desired effect. Control of the precipitation method may be possible through careful control of pH. BiFeO3 can be synthesized by sol gel methods both as fine powders and by control of sol viscosity as ultrafine fibers. It can also be prepared by hydrothermal synthesis and by combined microwave assisted hydrothermal synthesis at 200 degrees Celsius for 30 minutes. So these are the different techniques we have studied, and we have seen that these techniques are quite successful for the synthesis of many inorganic compounds. Although hydrothermal process occurs naturally in for the crystallization of many natural components, but scientifically it is discovered later and even implemented in the 19th century. This method is believed to be one of the most important and unique method for the successful synthesis of many compounds. Homogeneous liquid precursors can be used to produce powders by solution combination synthesis, which may be known as SCS, solution combination combustion synthesis, in which metal components, fuel, and even oxidizers are all present in the correct amounts in the precursor solution prior to ignition of self-sustained exothermic reaction to form BiFeO3 product. Crystallization of BiFeO3 from aqueous solution can be facilitated by the application of high power ultrasound waves with frequencies between 20 kHz and 10 kHz sonochemically. This technique is actually known as sonochemistry, and it is based on the acoustic cavitation resulting from formation, growth, and implosion of nanometer sized solvent bubbles in the precursor solution. Very high temperatures on a nanosecond time scale are generated during bubble collapse, and these are sufficient to break chemical bonds with precursor components, and which subsequently lead to the rapid crystallization of BiFeO3. Another method involving the formation of droplets within a matrix liquid phase is a preparation of micro emulsions, or we can sometimes say this is myceles. In the reverse micro emulsion methods, for the synthesis of BiFeO3, nano-sized water droplets should be dispersed in a continuous oil phase together with an surfactant. The water droplets containing precursor species act as a microreactor for the successful synthesis of BiFeO3. Here are some of the methods used to synthesize BiFeO3. The experimental conditions and the nature of the products are actually summarized in this table. In the synthesis method, we can see there is co-precipitation, microemulsion, hydrothermal, sol gel, microwave assisted hydrothermal, and mechanosynthesis. Here we can see that in co-precipitation method, the product size is in the range of 30 to 100 nanometer, while we are unable to control the shape in this method. The reaction temperature should be around 20 to 90 degrees Celsius in co-precipitation method. While this reaction usually complete in minutes and subsequent annealing will be held at 550 to 700 degrees Celsius. In the second method, which is microemulsion, the product size should be in the range of 15 to 40 nanometer, while its shape control is good in this microemulsion synthesis process. The reaction temperature range is 20 to 70 degrees Celsius and it usually complete in hours, while the subsequently annealing is done at 400 degrees Celsius. In hydrothermal method, the product size range is less than 100 nanometer in size, while the shape control is very good, and even in powders, spindles, and sometimes nano flakes, nano cones, nano rods, nano flowers, there are so many shapes can be formed by this method. In hydrothermal method, the product size and shape can be controlled. We can synthesize same shape and similar sized compounds products in uniform fashion, while the hydrothermal synthesis done at 150 to 200 degrees Celsius. The reactions time usually contains more than a day. It may occurs in hours a day, and sometime into 14 days are required for the hydrothermal synthesis, and there is no need of annealing because we are already using good and high temperature for a long period of time. While in sol gel method, the product size is in the range of 15 to 150 nanometer. The shape control in sol gel is good, and maybe the powders and fibers nanotubes are formed uniformly. The reaction temperature around in sol gel is around 20 to 90 degrees Celsius, while the reaction time may be comprises of hours or day, and there is the need of annealing which would be done at 400 to 600 degrees Celsius. It will depend upon some of the product compositions. Microwave assisted process, it is a process in which the product size less than 100 nanometer, and it is shape control is good in microwave assisted method. In microwave assisted hydrothermal method is actually the temperature range is between 100 to 200 degrees Celsius. The reaction times occurs in minutes, and subsequent annealing there is no need of annealing. While in mechanosynthesis the product size is same as in hydrothermal synthesis and microwave assisted synthesis. The shape control is fair. It's not very good enough to control the shape in mechanosynthesis method, while the reaction temperature is around 25 degrees Celsius, and the mechanosynthesis may complete in hours, while there is no need of subsequent annealing in mechanosynthesis method. The next one for after the synthesis of BiFeO3 by Camidose methods is the molten salt synthesis. It is also known as MSS. Molten salt synthesis uses low melting water soluble salts such as alkali halides, carbonates, and sulfates as the liquid medium in which one or more of the reactants are soluble, but the desired product is insoluble. The liquid assists rapid diffusion of reactant species at low temperatures, which is 300 to 800 degrees Celsius. It usually depends on salt composition and can give high quality product in a shorter time and at much lower temperature than achieved by solid state synthesis. At the end of the reaction, the molten salts at the end of the reaction the molten salts can be dissolved, leaving behind the solid product. There are two generally accepted mechanisms of molten salt synthesis, both of which are actually based on relative solubilities of the reactants. In dissolution precipitation, all the reactants dissolve initially and the product then precipitates. In temperature controlled growth, one reactant is insoluble and serves as a template upon which the product can form and grow. This is actually more controlled mechanism and can allow specific particle sizes and morphologies to be produced. Numerous mixed oxide materials have been produced by molten salt synthesis process. These includes lanthanum aluminium oxide formed after 3 hours at about 630 degrees Celsius in potassium chloride and potassium fluoride liquid mixtures, and magnesium aluminium oxide formed after 3 hours at about 1100 degrees Celsius in mixed chloride molten salts. So this is all about this molten salt synthesis and synthesis of BiFeO3 by Chemidos methods. Thank you very much.